Great, yeah, thank you so much. It's great to be here. My name is Stefan. I'm leading the quantum applications team at QuEra, and today I will present a little bit what we are working on in the application space, in particular in the pharma sort of realm. And today's talk, as the title suggests, will mostly touch upon the future, but I will also very concretely tell you how we're taking steps towards such a future at QuEra. And to start off with envisioning such a future, let's imagine it together, how it could look like. So for that, we have four people: Alice, Bob, Charlie, and Eve. And unfortunately for all four of them, they have a certain disease. Alice here has myotonic dystrophy and is getting weaker due to sort of progressing muscle loss that is associated with that particular disease. Bob, and the good thing is, like, Alice actually has an improved condition because there was a new drug discovered, which was designed based on a new, like, quantum-trained DFT functional that is now allowing us to, like, more accurately describe the processes that actually result in DM. Similar to Bob, Bob has an early stage, or had an early stage of Parkinson's disease, and it really started to affect his ability to move. But now he actually is in remission because a quantum computer helped us to actually understand the protein dynamics that results in the misfolding of the proteins that result in Parkinson's. And quantum computer really allowed us to develop a drug that can finally, like, relieve Bob. Charlie has Alzheimer's disease, which is a disease which is sort of similar to Parkinson's, and his memory is fading. And suddenly, now with a new drug, he experienced slow memory loss because a quantum computer was actually finally able to describe the binding of drug molecules to the metal centers in his amyloid beta protein, which are like the main driver of Alzheimer's disease. And like last but not least, Eve is actually in hospital with a very critical condition of pneumonia, but like no antibiotics helps. And the reason for that is because she developed antimicrobial resistance, AMR. But a quantum computer, again, allowed us actually to open new pathways to generate antibiotics because, like, we are able to kind of derive binding affinities of small drug molecules with different types of proteins more effectively now. So that's an amazing future we can envision. Unfortunately, I'm the one today who is here to tell you that we're not there. So we're working very hard, and there's a lot of hard work in front of us to actually get to such a future. But all the four use cases here, we believe there is a certain potential for quantum computers to actually get us to such a future. We are working on these steps within Wellcome Leap's Q4Bio program, which Shihan already presented earlier today, which is a 50 million supported challenge program funded by Wellcome Leap, where the ultimate goal is really to demonstrate that there is a place for quantum computing in these sort of fields, like for such a future. We are actually a little further than my line suggests by now, so sort of half into phase 3 of that program. And phase 3 is really the exciting time where we're starting to deploy things on quantum hardware. The whole program, as Shihan pointed out, started with 12 teams. 8 of them were left for phase 2, and now 6 teams are remaining in phase 3. QuEra is part of 3 teams in this program, and 2 of them are still in phase 3. So what that already suggests, since I'm talking about teams, we're not doing the work alone here. Actually, we're working with great collaborators on the myotonic dystrophy. We're working with the University of Nottingham, as well as with Facecraft, a UK-based quantum algorithms company. For the Parkinson's disease problem and the structural protein inference, we're working with Harvard, MIT, and the Broad Institute in Boston. For Alzheimer's, it was a collaboration with QBraid and the University of Chicago, again, within the Q4Bio program. And for the AMR problem, again, this is part of the Harvard, MIT, and Broad collaboration. So what are we actually doing with quantum computers for such a future? Where could quantum computers come in? And why do we actually think quantum computers can help? And the standard answer, which you hear, is, well, these are proteins and small molecules. They're nanoscale objects. Electrons are actually making them interact, and therefore we need to treat them quantum mechanically. Well, actually, that's not entirely true. Like, nanoscale and electrons being involved does not mean that you need to treat them quantum mechanically. For us as a quantum computing community, that's a bad thing, because quantum computers might not be necessary. For us as humans, that's a good thing because it means we have really good drugs right now developed with classical tools. But what it also means is that really careful target and use case selection is critical to kind of push this field in the quantum computing realm. And that's how we can really start to innovate as early as possible using quantum computers. But it's not really obvious how one would do that. How do you actually find the good targets out there? And I want to give you like 3 examples, and I will go over them rather quickly from our Q4Bio project, how we actually address this problem together with our collaborators. So the first example is actually in our collaboration with MIT and the Broad Institute, in particular with Jim Collins' groups and very talented drug designers, Andreas Lutens and Arthur Grisham, who actually helped us identify targets that we believe quantum computers can actually make a difference. So what we did there, or in particular, in this case, like our collaborators, informed by us as a quantum computing company, was like screening the protein data bank, which is the data bank where all the structural data about proteins and small molecules are stored, to actually search for certain compounds where we expect strong correlations to occur. And we had to pick something. So what we picked actually was like, we know from classical computational chemistry that iron-sulfur clusters are very hard to describe. They're very multi-configurational. So we actually decided to kind of, based on the fact that they are hard and known as a classic example of a strongly correlated problem, kind of filter down, like in the search space, based on this search criterion. And we started with 215,000 structures, and we ended up with 3 targets at the very end that fulfilled certain criteria we wanted to fulfill. So the first criterion was very obvious. We wanted to search proteins that contain iron-sulfur clusters. There were actually quite a few of those, like 3,000. But that was not enough for us for this project because we also wanted to actually design drugs. So we wanted also to have a reference where we know this protein does also interact with a small drug molecule. And then we are already only left with 800 structures. And then the interesting point is actually the very last step, it got us down to 3 because we said we want to have systems where we actually have data available, where people actually studied them either with classical computational methods or in the lab. And then we ended up with 3 compounds which actually fulfilled all those 3 criteria in this space. And one compound we were particularly excited about because it actually relates to antibiotics design, which is the use case we're trying to develop or understand. And it's quinolate synthase, NADA, which is sort of a known system, and like our pipeline sort of guided us to it. And it does have a very nice iron-sulfur cluster here in the protein binding pocket, and the iron-sulfur cluster directly interacts with a small drug molecule. And it is an enzyme which is involved in the biosynthesis of a coenzyme, NAD+, which is really important for bacteria to get energy to grow, basically. But humans can actually get this NAD+ through a different sort of pipeline, through vitamin B3 in particular, which means if we actually can inhibit this NADA coenzyme to not generate the NAD+, which the bacteria can salvage, we can actually slow down bacterial growth. So it's a different pathway to develop antibiotics. And it's really like the synthetic molecule interacting with this iron-sulfur cluster, which makes it a hard problem to design actually small drug molecules for this problem and to simulate it. And therefore, like we sort of have a certain target and a very specific use case how to solve Eve's AMR problem. And that is one example how we can sort of down select in the vast kind of space of potential targets to a system where we believe there is something for a quantum computer to actually do. An alternative is actually a slightly different approach, which is the one we are developing together with the University of Nottingham and Facecraft, which is more like enhancing more traditional methods which are employed at the moment in the drug design pipeline. And in our case, that's DFT, density functional theory. I will not have time to go through all the details here, but the core idea is basically that the quantum computer can generate data that are valuable to improve density functionals. And these improved density functionals can then be used to kind of feed into a more like standard classical pipeline, in this case, designing covalent inhibitors for diatonic DM. If you are interested, actually, there is a review paper summarizing everything that is shown here in more detail. And then last but not least, there is actually also something which quantum computers can do really well, and that's spin dynamics. And in fact, spin dynamics is also something we can use in the sort of pharmaceutical domain. NMR, low-field NMR experiments are basically spin dynamics experiments. And from the spectra we get out of NMR, we can actually infer protein structures. And here's just a very, very basic small example. But this is a type of Heisenberg model which describes this small molecule here. And now with like quantum dynamics, you can actually kind of find a spectrum, which is this orange curve here, which represents, like reproduces the target reference spectrum you know in this case, like because it's very easy to simulate. And from that spectrum, we can actually infer the structure of the molecule or the larger protein if we wanted to. And that's like referring to the Parkinson's disease example I mentioned in the beginning. Of course, like for these small toy systems, we can simulate this classically. But once we go to larger systems, I'm really interested in the protein dynamics by, for example, also docking fluorine onto these proteins and trying to study the dynamics. It's getting hard. So that is sort of using the native things quantum computers can do well to discover new drugs and protein structures in this space. But so these are three examples we're sort of exploring. But of course, the final question now is like, what do we do with those examples? How do we actually address these problems and solve them on a quantum computer? And that's what I want to like end my talk with. So when one starts to think in this space and like explore those problems on a quantum computer, very quickly one ends up with a list what a quantum computer can do and also what one can't do, but one should potentially do. And what a quantum computer can do, and that's something we all know, it really can capture the strong correlations that are part, like that these systems generate. But what it can't do is like really, for example, perform the high throughput screening of large kind of databases as we did here with the classical computers. Like it's just like quantum resources are sparse, so we should not like really use them for like large screening problems. What it can do as well is really model the dominant factors of the quantum mechanics involved in this binding problem. But it cannot just kind of estimate all the entropic binding, like molecular dynamics and sample over many geometries, because again, for the same reason as the one above. And therefore, it maybe is also more like a way to indicate certain small mechanisms, why a certain drug works better versus another, rather than being a full predictive quantitative tool. And related to that, actually, a quantum computer will not be able to really simulate the entire protein binding pocket and the small molecule on a really atomistic model. We will always have to do some approximations to actually come up with a solution. And based on that, and based on that, I think we ended up with a very clear pipeline how we can solve those problems on a quantum computer. And it sort of involves 3 steps, and all of them are equally important. The first step is the pre-processing step, which actually happens on a classical computer. And I gave you some examples how we actually pre-process the problem, sort of. Then we move on to our neutral atom quantum computer at QuEra, and there we like employ this notion of co-design. We try to already pick the problem which we think where we can leverage the strengths of our hardware very well. But also more importantly, by working in this space, it even informs us what we have to improve on our hardware to really tackle these problems moving forward. And then the last step, which is also critical, is what we call post-processing. And that, again, happens on a classical computer. And post-processing is just meaning we have to extract information, mitigate errors, error correct, detect, and so on. So just some very brief examples how these 3 steps will look like. For the pre-processing step, basically the idea is just using as much as we can from the classical world. There are really good classical techniques available, and we can use them to pre-process our data. And one example is actually trimming down the big problem of the big binding pocket into a smaller model. But more importantly, actually, is what we call downfolding. It's really reducing the qubit count we need to describe those models. And here is just a very small example based on hydrogen, where we sort of developed this in-house pipeline, which allows us to go from a very large basis set into a smaller basis set without losing accuracy, which means a large basis set to small basis set means like reducing the qubit count. So for H2, for example, we reduce the qubit count by 12 qubits, but actually you see like the curve, the orange curve of the downfolded Hamiltonian is pretty much on top of the CCP-VDC basis, which is like the very accurate basis. So the dynamic correlations, which play a crucial role in this binding process, are actually taken into account properly. And then once we have this system, it's all about co-design, which means maximizing the impact of our core strengths. And in neutral atoms, there are multiple, but I think there are 2 really important ones, which is the all-to-all connectivity and the parallelism, which means we can really design new types of procedures to prepare states and ansatz, which we can actually use to prepare states more efficiently than on other platforms. And just a very brief example, we do have a new neutral atom-inspired ansatz for these types of problems, which really significantly reduces the circuit depth for ground state preparation. Just as an example, it reduces the qubit count from a UCJ, a Jastrow ansatz, almost by a third. So from 92 qubit gates to 36, and this is for a hydrogen 4 chain in a minimal basis set. But as you see here on the right, actually, it's not so different in terms of actual error you get compared to the deep UCJ circuit. So what that basically implies is that neutral atoms really allow us to generate the correlations needed to build up the entanglement or for these systems much more efficiently because we have this all-to-all connectivity. That's basically the upshot of this. And in the last step, maybe just very briefly, post-processing is all about knowing your noise, like knowing what your quantum computer does not do so well, which allows you to post-select and also mitigate certain errors. And just a brief example, again, this is for a very small simulation, again, on a laptop for a 6-spin Heisenberg chain aiming towards this NMR problem. You can actually run, since on neutral atoms we actually also have many qubits and we can like waste some qubits for additional circuitry, you can run some small additional gadgets on top of your circuit. In this case, it's 1 ancilla per spin to actually read out information which qubits could have been lost during your simulation. And you can post-select on those data, and you really see that by post-selecting, you basically get back on top of the exact result you expect. And then you can also start adding like more circuit level noise. All of you can actually do that by just scanning this QR code and using our blockade infrastructure. And one can actually analyze more how other types of error sources can be mitigated. And it's a very exciting time at QuEra because we're actually ready to deploy all these sort of techniques and insights on our new gate-based machine, which is installed at ICE in Japan. And I guess next year at that time, or even a little earlier, I will be able to show you amazing data from this new machine, which is set up in Japan now. I want to like maybe spend 1 minute to actually also tell you, as we heard already, drug design is not just about biochemistry. It's sometimes also a data science problem. And there is this quantum reservoir computing work we did actually together with Merck, as we just heard, which sort of is interesting because it sort of uses the quantum computer in a non-trivial way, in a sort of a non-linear map. And I don't want to go into too much details because you just heard a talk about it, but it is another way of thinking about innovating in the drug design space, is actually reformulating the problem as a data science problem. And with that, I'm pretty much at the end. I think what I showed here really shows that collaboration with domain experts matters in this space. The reason I was able to kind of talk about these things is because we were interacting with many different experts from different fields. I already mentioned all our nice collaborators, but we are always happy to collaborate with more of you. So please reach out or talk to me if you have ideas. We're happy to talk and add you to this list of great collaborators. And by that, we can then actually build such a future together, and maybe even better than what I was envisioning here. And with this, I'm at the end, and I'm looking forward to questions. Thank you.
Thank you very much. Do we have any questions?
Thank you for the great talk. I have a question about the NMR use case. So you specifically select the low field NMR because otherwise effects get washed out, right? Do you have an idea on how large of a coherence you get in spin dynamics on NMR and for proteins, for instance?
Yeah, so NMR in that sense is a very interesting field because, as you mentioned, like the typical high field NMR, it's actually pretty classical. Mean field will solve it, basically. And then you have to go to the low field, and also like it depends a lot on the protocol you choose. So to some extent, I feel NMR has a little bit of a chicken and egg problem because many of the protocols were developed having classical computers in mind, right? So actually the main target was classical interpretability of the spectrum. So it could be that actually showing that we can now generate spectra more efficiently with a quantum computer might allow us to develop new protocols we don't know right now. And that is actually, I think, the path we should take. Many of the traditional protocols, actually, I agree, are pretty classical, But I think that's where this could come in to actually demonstrate there is something there, and then we can sit down and think what is a good protocol to really kind of have better NMR data. Yeah.
So do you mean like pulse design or stuff like that?
I mean, it's about the pulse design, but it's also about like how low in field do we have to go. Also, like how you prepare your sample. So I mentioned these fluorinated proteins actually can dock sort of metals as well. So then it gets more strongly correlated, and the dynamics gets harder. So it's like multi-layers. It's the pulse, it's like the field, and it's also like how you prepare your sample actually. Yeah.
Maybe I have a question. So you presented these error mitigation protocols. How do you envision them working with error in a fault-tolerant regime, so with error correction?
Yeah, that's also a great question. I mean, the way I see these types of error correcting or error mitigation protocols, it's almost like an interpolation step. Because actually for this one, we use a whole register of ancillae and like entangle them with our system and then read out the ancilla and we can tell you which qubit got lost, right? So it's not an error correcting code, but it sort of is a way of using ancilla-based kind of circuitry to kind of inform you about the actual system. It will not like extend, like these things are built into error correcting codes as soon as we kind of move into true encoded circuits. But actually, like in a sense, the subroutines will be similar. We again will have a qubit register, which is our ancilla register. We will like let it talk to the whole system. In this case, in the error corrected case, it's a little different because we have to extract the stabilizers, right? It's more non-trivial in terms of what circuit we will have to run. But it's sort of a step towards that in a sort of a NISQI type of flavor.
So it's like an intermediate
it's sort of an
regime.
intermediate way of doing it, yeah.
One last question? Okay, if not, let's thank Stefan again.